So a natural follow-up is, suppose I consider a slightly different network, R1 in series with R2 and R3 in parallel.
Yes,
right?
Now we come back to the question you are asking.
Right?
Right. So now I will take a resistor and you wanted something in parallel, right?
Yes.
Yes. So this is a combination of the two networks. So previously we saw series and parallel, but now we are using a combination of the two. Okay.
Right.
So this is my two wires that is coming out of the black box.
Yeah.
So R1, R2 and R3.
R3.
Okay. So I want to find out the equivalent resistance between these 2 points.
These 2 points. So my question is, first of all, is it wise to go down the same path of doing VDC by IDC, or should we be doing something else here?
Good point. We should be able to simplify the network.
Okay.
Because at the end of the day, if you want to find out only equivalent resistance, what we are already saying is that we are only interested, we are looking already at this as a black box. Right? We are only interested in what happens at these two terminals.
Correct.
So we should be able to simplify the network.
Network itself, right? Okay. So, so for example, in this circuit, right, is it, suppose we just looked at R2 and R3, and can I ask what's the equivalent resistance of that subset of the network?
Yeah, I think that's a good way to start. So what we can do is, we can start identifying what techniques, how the simpler circuits that we saw, and figure out how to apply.
Yes.
Clearly the easiest thing to start off is R2 in parallel with R3.
R3.
So let us do that. So we can simplify this network to R1 remains the same. We are not doing anything. So we are only going to take this portion and make this, we know that two resistors in parallel appear resistive again with an equivalent resistance, I think, which is 1 over R2 plus 1 over R3.
Yes.
So we will write it like that.
So,
So maybe I'll start naming these nodes N1, N2.
Correct.
So that we keep track of, and maybe I'll call this N3.
Yeah, absolutely. Yes.
So this is N3.
N3,
Nodes N1, N2, N3 are defining the network. So I am going to call this R equivalent 1.
Yeah, right.
Or maybe R equivalent 2, 3.
2, 3, exactly.
2, 3.
Yes.
Okay. And I think we saw that if you have two of them, it is the inverse of that.
Exactly.
And that can be actually simplified.
As R1, R2 by R1
plus R2.
Okay.
Right? So in our case, we will basically have R2, R3 by R2 plus R3.
Yeah. So it's effectively like putting an ohm meter across R2, R3 combination in parallel.
Exactly.
Because no current will flow through R1 now.
Yes,
right? Because that's an open circuit.
That's an open circuit.
Right.
When we are measuring only across N3 and N2, we will leave N1 and N1 open. So there is no current in that
No current that can flow, because any current that flows out has to come in somehow.
Correct. Currents always flow in loops.
Yes. Right.
That's right.
So therefore, it's like saying putting the ohm meter there, and that will tell you R equivalent of R2 and R3.
That is correct.
Right.
That is correct. So it is like adding a VDC from here to here.
Okay.
Okay. And that is what we have made into this R equivalent.
Okay. So,
there is of course no current here.
There's no current there, right? And then you're saying now you add the VDC to this N1 and N2.
Right. So now that we have this R equivalent 3, so I'll call this VDC 1.
Yes.
Now I can add VDC 2 here.
Okay.
So we are now doing it in stages.
Yes.
I'll add VDC 2 here.
Yes.
Right?
Yeah.
And now I know that there will be some current IDC2, but actually I already recognize this circuit. This looks like a series combination of, it's the first circuit that we did.
Looked at, yes.
The series resistance is nothing but the sum of the two resistances.
Two resistances, right? So that is just going to be R1.
So this R equivalent, so this is R equivalent total, right?
Yeah.
R equivalent is the sum of the two resistors. The first one is R1, the second one is
R2,
R equivalent 2, 3.
Yeah. Correct.
So this is nothing but R1 plus R2, R3 by R2 plus R3.
R3.
Nice. So this seems to be a resistance as well.
Yes, it is a resistance, and so in some sense, the analysis we are trying to do is we don't have a voltmeter or ammeter, but we are just trying to look at the network and actually guess and find out what the equivalent resistance is.
That's correct.
Right? Okay. So this is nice. So maybe the natural thing would be to sort of get into more complex networks, right?
Maybe shall we try the reverse of the two? This looks like you have placed one series and two in parallel.
So R1 in parallel with R2 and R3 in series.
That's right.
Okay, let's
Shall we try that?
Great idea.
That's a slightly different variation of the same problem.
Correct.
So what I'm going to do now is I have R1.
Yes.
And I'm going to create the series combination of R2 and R3.
Yeah.
So R1, R2. Is this what you are thinking of as well?
Exactly.
Perfect.
Great.
And now this would be my two
nodes.
Yes. So I'll call this N1, N2.
Yeah.
And now I have the third node N3 here.
Correct.
In between the two.
Yes.
And again I'm interested in this black box now.
Yeah.
Right?
Correct.
This is now my black box. I want to find out the equivalent resistance across N1 and N2. Right?
R equivalent. Right? Yes.
So again, shall we start by identifying the things that we have seen before?
The subset that we have.
The subset.
Yeah, exactly.
I can already see R2 and R3.
R in
that is the first thing that seems to stand out.
Correct.
Right? So maybe I don't have to show, but I'll just point out imagine there's an imaginary VDC I connect here.
Yes.
I find out the current taken by that and so on.
Yeah.
But now we can start imagining this in our minds. We can just apply the principle. Right? So what I will do, I will say that this portion now gets transformed. So the first portion remains the same, which is R1.
Yes.
And the second one gets transformed into an equivalent resistance. So this had R equivalent 2,3. And that resistance comes over here.
Yeah.
And we know what that value is. That is exactly equal to R2 plus
R3.
Because they are in series.
Right?
And now I can complete the rest of the network, bring out the two black box nodes.
Yeah. So we have to keep that intact. That's the only thing, right? Yeah.
By the way, I noticed something. When we are finding out these equivalent resistances, we seem to be losing some nodes inside the network.
Right? Exactly.
N3 seems to be missing in this equivalent network.
Yes.
And even in the previous one, I remember N3 was there, but eventually when you find R equivalent, N3 is gone.
N3 is gone, right? So it's okay to lose those nodes.
It's okay to lose those nodes because we are interested only
in N1 and N2.
N1 and N2.
Absolutely.
Right? That's why we said black box.
Black box, yes.
Okay.
Right. So therefore, between N1 and now I can recognize this. It's R1 in parallel with R equivalent 2,3.
That's right. So we'll say that it is R1 in parallel. So maybe I'll use some notation.
Notation like this,
right?
Yes.
To show that they are in parallel.
Yeah.
Right? So we know what this is. So I'll show this in this form 1 by R1.
Yes.
Plus 1 by R equivalent 2,3. We know what that is. So that is 1 by R2 plus R3.
Yes.
Because R equivalent 2,3 is R2 plus R3.
Yes, exactly.
So 1 over that.
Exactly. Right? Okay. So the idea is to first identify a subset of the network that we recognize.
That's right.
Replace that with the equivalent resistance, then come one level above, replace that, and you keep going like this.
That's right.
Eventually, until you get to the two nodes that you are interested in.
Absolutely. And by the way, I also remembered one more thing. I remember, when I was studying, a lot of exams used to trick students.
Okay.
Right? Because we have drawn it nicely such that they are able to see series, parallel nicely.
And all that.
But for example, I have 3 nodes.
Yes.
I can make a triangle.
Oh.
Right?
Okay.
I can redraw it in whatever way I want. So for example, I have 3 nodes N1, N2, N3. Right? I only have 3 nodes. So I'm going to draw it like this. Right?
Okay.
I take these 3 nodes. I have R1 between N1 and N2.
Yes.
So I'm going to show R1 here.
Okay.
Like this. R1.
Yes.
R2 between N1 and N3.
N3.
Okay. So I have this R3. And then R2 between N1 and N3.
Yeah.
And R3 between N3 and N2.
Yes.
Right? So that's here.
Absolutely.
So as you can see, there are ways to trick students into not seeing exactly. So now it's a little bit harder because now I want to find out R equivalent across these 2 points.
Wow. Okay.
Right?
Yeah.
Now it's a little bit harder to visualize.
Yes.
Because we have changed the way we have drawn
it. It's
right?
actually the same thing.
It's actually exactly the same circuit,
thing.
right?
Okay.
Exactly the same circuit because I only have 3 resistors, 3 nodes, R1 between N1 and N2, R2 between N1 and N3, and R3 between N2 and N3, and I've just redrawn it.
Okay.
Right? I could have redrawn, see, it is all happening inside the black box. All I'm doing it is pulling out 2 nodes, 2 wires.
Correct.
Right?
Okay.
And,
this is interesting.
Yes. So students need to be able to imagine, maybe redraw in their minds.
Redraw in their minds, or the way to foolproof way of doing this is the current entering R2 has nowhere to go but to go through R3, and therefore they have to be in series.
Perfect.
Right?
Perfect.
Okay.
Okay. So if you can identify those simple, pieces, so you can clearly see that N3 is connected only to R2 and R3, like you said.
Yeah.
Right. So these 2 have to be in series.
Have to be in series.
Perfect.
Right?
Perfect.
So that's how we are going to analyze. So apart from all the concepts, you might have to redraw this a little bit to keep it comfortable for yourself.
Absolutely.
Right?
Absolutely.
And the only way to solve these problems is by practice. Right? You just look at numerous problems.
Yes.
Okay.
You have to solve as many problems as possible. And in fact, simple resistive equivalent circuits are actually quite common. You will see them in many textbooks. And you will find a lot of practice problems. And we will indeed give practice problems to the students as well.
In the tutorials as well.
Yes.
Okay. So why don't we now proceed to like more complex.
Even more complicated ones?
Yes.
Okay.
Complicated networks.
So,
right? Okay.
Maybe
so
give me some ideas. Okay. So now you're going to test me from the textbook.
Yeah. Okay. So, so can we try this problem?
Okay.
There are in fact values also here.
Okay.
So we'll actually keep the values because I think that's also going to help us.
Yes.
So I have a 5 ohm.
Okay.
So let me tell you,
so
I have a 5
I'll start from N1 and come to N2, right?
Yes.
So you can now see.
I'm going to tell you N1.
I'll start from N1.
Yeah.
Okay.
So there is a 5 ohm.
Okay.
Okay. And you get a new node, let's say N3.
Okay.
Okay. Between N3 and N2, there is a 30 ohm. Yeah.
I'll show N2 here.
Yeah.
And this is a 30 ohm resistor.
Yes. Right. Then between N3 and N4, there is a 20 ohm.
So there is a series 20 ohm.
Yes.
Okay. This is N4.
And between N4 and back to N2, okay, you can just draw that as a straight line, and that is 200 ohms.
200 ohms.
Okay. And between N4 and N5.
There is another node. Okay.
Yes.
This is now getting complicated.
Yes. 30 ohms. Okay. And then there is from N5 to N2. You are back to 20 ohms.
Back to 20 ohms.
Okay.
Okay.
So how do we solve such a problem?
Okay. So by the way, I already noticed because we talked about redrawing the circuit.
Yeah.
I can already imagine textbooks. I don't know if the textbooks really did this, but you can see it is easy to redraw this resistor like this with a triangle.
Yeah.
Right? You can see there is a common node across. You could have redrawn this 200 ohm as well like this.
Correct.
Right?
Exactly.
You can find out all many different ways. But the real thing is that what matters is that the as long as the connection positions of the resistors between nodes is the same, the circuit is the same because the voltages and currents distribute in a specific way.
Okay, right.
Okay.
Okay.
So maybe let's start by identifying simple patterns.
Yeah.
I can already see some. So one thing I like to do is to sometimes start far away from N1 and N2.
Okay.
Right. Because it gets complicated. I noticed here in the techniques that we did.
Yeah.
I didn't start directly with R1.
Yeah.
I did simplified the other parts
Something
first,
else, yeah.
and then came to R1.
Yeah. So
and I noticed the same thing in this problem as well.
Yeah, we solved R2, R3 first, and then we
went to R1.
Okay.
So maybe what I'm going to do here, I'm going to try further away from N1 and N2.
Yes.
I'll start from the rightmost side.
Okay.
Because I also identified those two are in series.
Yeah.
So maybe it's
current coming into N4, right? Out of N4 into the 30 ohm has nowhere to go because N5 is not connected to anything else but the 20 ohm resistor.
That's correct.
So therefore, that's a series combination.
That's a series combination.
Okay.
That's right. So I know that this current is equal to this current.
Yes.
I know that this 30 ohm and this 20 ohm are in series.
Yeah.
So I know that this portion of this network is equivalent to an resistance
with
that has the value which is the sum of the two resistors.
50 ohms.
So which is 50 ohms.
Okay.
Okay.
Great.
Now I need to identify the nodes.
So so this is like what between
N4 is easy, that is the left of 30 ohms.
Yes.
The other side N5 is gone.
N5 is gone.
And then other side I've actually come to N2.
N2. Yeah.
Okay.
So maybe in the initial stages, it's recommended that students redraw the circuit at every stage.
Absolutely.
Right?
Very important.
Don't mentally assume. Yeah. Okay.
Don't start doing it.
Why don't
mentally.
we do that also?
We'll do that as well.
Right?
Yes.
Okay.
So now that I have done this,
Yeah.
I can now, this circuit gets transformed in this fashion. So I have the 5 ohm.
Yeah.
I'll put in the values later.
Yeah.
This is the 20 ohm.
Yeah.
I have the 200 ohm. And now, so now I'll put in these values and put in that transformed network at the end.
Correct. 20 ohms,
200 ohms. So N1,
N1,
N2, N3 and N4.
Okay.
And now that portion has now become a 50 ohm resistor from
between
N4 to
N4
N2.
and N2. Okay.
So it
Great.
becomes like this. Right?
Okay.
Perfect.
So now I can see that the 200 ohm and 50 ohm seem to be in parallel because the potential difference across the two resistors are the same.
Correct. I have a loop here.
Yes.
Which has, which shows that the potential drop across the 200 ohm and the 50 ohm is the same.
Same, right?
Right.
So therefore we can replace that by a parallel.
They are in parallel.
Equivalent resistance.
Correct.
Right?
So now I'm going to simplify this portion.
Yes.
So this portion's resistance, I have a 200 ohm and a 50 ohm in parallel.
Yeah.
So I will say that that is also equivalent to a single resistance
With
whose value is 200 into 50 by 250. Right?
Yeah.
So
10,000 by 50.
So that's 200. Right?
Yeah.
So 200 into 50 by 250.
Yes.
250 is 10,000.
Yes.
So 10,000 by 50
By
is
250.
1000 by 5, which is 200.
40 ohms.
200 ohms, right? Oh, sorry, 40 ohms.
40
Sorry,
ohms.
not 200 ohms. 40 ohms.
Yeah. So the first thing in a parallel combination is the net resistance has to be less
That's
than
right.
both.
That's right.
It has to be less than both R1 and R2.
Correct.
Right? So
in fact, that should be seen from the original parallel resistance
correct.
equation that we did. Right?
Yes.
This shows you that the inverse of the equivalent is the sum of the two inverses.
Yes.
So you can show that this R equivalent will always be smaller than both R1,
and R2. So that's
right.
the first check that
That's
we need,
correct.
right?
In fact, so then similarly in the series case, right,
has to
the
be
equivalent
greater
resistance is always larger
than both.
Than both.
the each individual resistance.
than each individual resistor.
Right, exactly.
Correct. Okay. So
Right.
that's a good sanity check.
Okay.
So in this case, so we said that this is 10,000 by 250, which is
40 ohms.
1000 by 5. Sorry, 1000 by 25.
25.
Which is 40 ohms.
40 ohms.
Right?
Okay.
Perfect.
So now we redraw this network
We redraw
again.
this network again. Okay. So I'll move to the next page.
So you have the 5 ohms.
5 ohms and 30 ohms. So okay, and then I'll add 20 ohms, 2 and 4. And what I have done is this portion I have replaced with a 40 ohm resistor.
So the N4 node still remains.
N4 node still remains,
Yeah.
but from N4 to N2 now I have a single resistor.
Yes.
Which was 40 ohms.
40 ohms.
Perfect.
Okay. Now I can see that the 20 ohm and 40 ohm are in series again because the current has to be the same through them. Yeah.
Correct.
Perfect.
So now this portion is 2 series resistors, so it's a single resistor of value 60 ohms.
Yes.
20 plus 40.
20 plus 40.
So
right.
now,
Again, we redraw.
correct. Go through all the steps again. It's always useful. So 50 ohms.
No, 5 ohms.
Oh, sorry, 5 ohms. So that's another important thing. You need to make sure there are no silly mistakes.
Yes.
Right? When you're redrawing. 5 ohms. I have N3.
Yeah.
And then now between N3 and N2, I created a 60 ohm.
Correct.
Right? In this case, it was across N4 and N2.
Yeah.
Okay. So now between N3 and N2, I have created a 60 ohm resistor.
Resistor, right?
Perfect.
Excellent. Okay. So now the 30 and 60 seem to be in parallel with each other.
Correct.
Right? So we reduce that.
So this portion is between N3 and N2. It's a single resistor. We said it has to be smaller than
30
each
and
of these,
60.
30 and 60. And the value is basically 30 into 60 by 30 plus 60.
Yeah, that is 90.
1800
right?
by
20
90.
ohms. Yeah,
20 ohms.
20 ohms.
Okay.
Excellent. Okay.
Perfect.
And finally, yeah, so let's not jump the step. We'll draw it again.
Yes.
5 ohm in series.
So I start from N1. So 5 ohms.
Yeah. In series with a 20
So
ohm.
I have N3, I believe.
Yeah.
And with a
20 ohm
20 ohm resistor.
Yes, absolutely.
To N2.
Yes.
Sorry. 20 ohm resistor to N2.
Yeah.
And now I know
Is a series combination.
this is a series combination. This has now become trivial almost.
Yes.
So this now becomes from N1 to N2.
25 ohms.
25 ohms.
Okay. So I think
this is clearly the equivalent resistance.
right. So
Right?
Yeah.
So going through these steps actually gives us a good idea of how to apply this.
How to apply this?
Right.
Yeah, and there are no shortcuts. Do it step by step, diligently, redraw the network. So can you go back to the original, because so when you present it with such a big network, it always helps to see if there is some sanity check that I can do, right? For example, right? What should my answer be, right? Can the answer be like 60 ohm? Can the answer be like 1 ohm, 2 ohm? I think we need to have some bound, so that we know we are on the right track, right?
That's right.
So for example, here I can see from N3 and N2, right? Going into N4, right? There is some equivalent resistance.
This portion.
Exactly. There's some equivalent resistance.
That's right.
Which is in parallel with a 30 ohm.
That is correct.
Right? So the net equivalent resistance there has to be less than 30 ohms.
That's right.
Straight away. And
That's right.
it is in series with a 5 ohm.
Correct.
So the answer has to be above 5 ohms first.
Correct. And less than 35.
Less than 35.
That's right.
So straight away there is a guess of where the right answer should be.
Correct.
It happens to be 25 ohms.
25
here, right?
ohms in our case.
But if you get 40 ohms, you know that
We know that we are in trouble.
you're in trouble, right?
That's right.
So these are useful sanity checks that you can make even before you get started. And I think it's important. In some cases it may be hard, but where possible, students must try to make this guess,
Absolutely.
right?
Yeah.
Okay.